I'm starting to record. So because of our crazy congressional FERPA regulations, students have to appear anonymously or not and invisibly and silently. So use the chat. Actually, the chat is not on the shared screen, so you can probably get away with speaking on chat in your own voice. Also, this Zoom window, I appear in it, but I don't think it is it recorded? Okay, guys, first of all, quick, somebody send me a chat message. Are you seeing the whole screen? And can you also see this if I click on it? So can you? Yes, you can see. All right, thank you. And it is recording. All right. So let me go back to kind of where we left off, which was basically we were talking about ghost contours. I thought I'd do one more ghost contour, but if somebody wants to see a ghost contour, then you know, speak up, and if we have time, maybe we can do such a ghost contour. I've got an awful lot of ghost contours here. People go nuts about ghost contours. You see, it used to be that we didn't have any computers or at least any that worked. And the result was that being able to do integrals analytically was very, very important. Now we can just essentially take any mathematical problem that's clearly defined and has a finite number of variables, and we can just throw it into a computer and write a program in Fortran C or use Python or Mathematica, MATLAB, all kinds of things. We can actually do them. But nonetheless, let's do one more example here. So let's get the inverse Fourier transform of Laplace transform, sorry, of 1 over s minus k. And what we do is we use this formula that was equation 4.147. So let me show it to you again. Looks like that. And so what we do is we see that our inverse Laplace transform of f of s, what we do is we change s to s plus iu, and we do an integral du, and then we get an e to the st here, and the du integration, we make sure we do it somewhere where the integral converges. And so we're going minus infinity to plus infinity du, and here we have f of s plus iu is just 1 over 1 over s plus iu minus k. And so we've got a pole there at u equal to I times s minus k. And we can add a ghost contour in the upper half plane, which actually does converge. You might think it doesn't, but it actually does. It converges because t is positive. Remember, Laplace transforms are for positive t. So t is positive, and this decreases exponentially in the upper half plane. Then we've got the two parts at the far end, and those two parts are a finite length, say length c, but they're divided by u, and u is huge because u is minus r and plus r. So those things also go away. So it is a ghost contour. And that means we just have the pole here at I s minus k. So we place u by I s minus k, and we get e to the kt, which is what the Laplace transform of this actually is. So you see, we get the right answer. Okay. Any questions about that? All right. So let me see. By the way, let me just mention something. How can I get rid of that stupid calendar? Oh God, I did the wrong thing. Ay, 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 ay. Okay, we're back to normal. In order not to have too many files that you had to look at and that I have to move and put links to, I decided that I would just keep augmenting, at least throughout chapter 6. I'm just going to keep augmenting this same note. So it just gets longer. And so the fact that you don't see a new note written down, a new note on the class webpage, doesn't mean that I've thrown away the new notes. It's that they're at the end of the third note, which is stupidly labeled September 23rd. I'm going to, I think, change the names of those things so that they're more sensible. Okay. So let me get back to the next topic. And the next topic is very simple, but it has all kinds of ramifications. And that's the funny thing about mathematics. You have simple observations, and then before you know it, they have unforeseen consequences. So a function, of course, is single valued. That's by definition. It maps every number z into a unique image f of z. So a function f maps z into f of z. That's unique. On the other hand, it's not sometime, okay, so the nicest kinds of functions, the ones we really like, are the ones that are one-to-one, because then we can relax because we know that for every value of f of z, there can only be one z that f maps from z to f of z. So that's one-to-one. Then you have a well-defined inverse and everybody's happy. Well, unfortunately, not every function is one-to-one, and things get worse on the complex plane. And in particular, that ambiguity affects the exponential function, and the exponential function is used to define a host of other functions in mathematics. And so the ambiguities associated with the exponential function then cascade throughout mathematics. So let's look at the exponential function. If we're just talking about e to the x for real x, well, there are no problems. The e to the x maps any real number into, of course, a unique number, e to the x, but the inverse of any positive number, e to the x, is the log of x, and that's well defined for positive numbers. The problem occurs when you go to the complex plane, because you see e to the z plus 2 pi ni, if n is an integer, is the same thing as e to the z. And consequently, there are many numbers in the complex plane that the exponential function maps to the same number, e to the z. And so it's not just 2-to-1, it's infinitely number. There are infinitely many z's that get mapped into e to the z And so there's no inverse exponential function. And in particular, if you take the logarithm of e to the z, you get z plus 2 pi ni, and n can be an arbitrary integer. By the way, there is this, in physics departments, we frequently like to distinguish between the natural logarithm and the logarithm to the base 10, and so we write the natural logarithm as often as ln. Mathematicians don't do that. They say there's only one logarithm and it's the inverse of the exponential. And if you want to talk about logarithm to the base 10 or 2 or some other crazy number, use a subscript on log. And that's probably a better definition. So sometimes in this book, I use log to mean natural log. And that's actually the convention in mathematics. And so in MATLAB, and I think also in Mathematica, log means natural log and not log base 10. Anyway, so the logarithm of a complex number gives us, gets us back z. And if z is r e to the I theta, then the log of z is the log of r plus I theta, where theta is you can call it the argument of z, or the angle in the polar representation of z. The trouble is that the polar representation isn't unique, because you can use 2 pi, theta plus 2 pi n, and both of them give you the same z. So z is r e to the I theta. It's also r e to the I theta plus I 2 pi n. And so the natural log of r plus I theta plus I 2 pi n is the correct value for log of r e to the I theta for every n. So we've got this this ambiguity here, and people then have learned to cope with it, and the way they cope with it is to establish a convention. And let me give you 2 conventions for where we're going to put theta. In other words, if we say here that, so let me use black here for the moment. And I don't know how I get rid of that damn thing. Oh, okay, but then I made a mark. Anyway, so what we're saying here is z is r e to the I theta. And so how do we choose theta? And there are 2 popular conventions. These conventions are semi-universal. One of them is that you put the cut, and the cut is sometimes represented by a dashed line or by cross marks like that. There, what you do is if z is real, then you can have theta equal to 0, or theta can be equal to pi, and then so for theta equal to 0, you're down there. For theta equal to, and if z is negative, you're over here, and basically you increase theta from 0 to 2 pi, and of course, what happens is you don't want to actually hit 2 pi because then you've got, you've lost uniqueness. So what you do is you have theta going from 0 to 2 pi minus epsilon here, or minus delta. And so that's one convention. This thing here is called a cut. And it's the line that one uses to make the distinction. Over here, we've put the cut on the negative real axis. And that's the other convention. So then, if you have numbers that in which the real part is positive, so you're over here somewhere, then theta has a sort of natural value. It's positive. Here you have z equal to r e to the I theta, and r, of course, is positive. And here in the upper half plane, you have theta less than pi and greater than or equal to 0. Down here, you have theta greater than or equal to, oh, that's minus, yeah, right. Theta greater than or equal to minus pi and less than or equal to 0. And so what you do is you have the cut down here on the negative real axis, and that's the other convention. So there are basically then two conventions. Sometimes you put the cut in another place. You can put the cut, after all, this is just to say, how are we going to define the angle theta? And we can always change theta by 2 pi n. And so as a result, you can put this line where you make the thing single valued. In other words, if you adopt the top convention, then you've made for any z in the complex plane, you know what theta is, what r and theta are. With this convention down here, you can, whoops, sorry, I wanted to get rid of that thing. Oh, over here, if you get this convention, then you can, for any z, you know what, r, of course, is just the distance from the origin. But the angle theta, well, you know that if it's in the upper half plane, it's well, they both have the same definition for theta if z is in the upper half plane. It's when z is in the lower half plane that they differ. And for the lower half plane, with this convention, the angle is greater than pi, and so it's pi plus pi over 2 down here. And on the other hand, for the second convention, the angle down on the negative imaginary axis is minus pi over 2. Okay, so those are the two popular conventions, but one can do other ones. And of course, the reason why this is a serious issue is that the logarithm is used to define many functions in mathematics, and in particular, z to the a. In other words, the complex number raised to the power a is e to the a log z. And so that's e to the a log of the absolute value of z plus I theta plus I 2 pi n, because theta is not unique. And so when you multiply through by the a, you get r raised to the power a, e to the I a theta, but then you get this non-trivial phase factor now. It's e to the I 2 pi n a. Let me grab my coffee, actually. My Leiden mug. So z to the a is not unique unless a is an integer. And of course, we know that z squared, z cubed, z to the minus 5, these are all unique. These are all 1-to-1. But when a is 1/2 or something else, we have to think about what's our convention for theta. So the square root, for example, would be, we take this formula here and we get, we set a equal to 1/2, we get e to the 1/2 log r plus I theta plus I 2 pi n. So the first two things give us what we expect, and then we have e to the I n pi. but e to the in pi is minus 1 to the n. So we've got basically that the square root of z is plus or minus, it's plus or minus square root of r e to the I theta over 2. And it changes sign whenever we cross a cut. So the square root of z is going to change sign as we go across this cut or that cut. And with the mth root, it's more complicated because we have the mth root of z is z raised to the power 1 over m. And so that's e to the 1 over m log z. And so this changes by 2 pi I plus or minus 2 pi I over m when we cross one of these cuts. If a is a complex number, say a is u plus iv, then z to the a is e to the a log z, so that's e to the u plus iv times this general value for log z, natural log of r plus I theta plus I 2 pi n. And some of these terms collect in a simple way, r to the u plus iv. But then we've got these surprising terms, which are e to the minus v plus iu times theta plus 2 pi n. So that means that in this case, when if you raise a complex number to a complex power, the ambiguity shows up in the magnitude as well as the phase. And so the way it shows up, so in other words, it's, well, as you see, it shows up in basically this 2 pi n factor multiplies minus v plus iu. And so as you cross a cut, we get a factor of e to the 2 pi minus v plus iu. Okay. This is sort of interesting. In other words, if you put the cut on the square root on the negative real axis, then an explicit formula for the square root of x plus iy is, and you might say, boy, that's kind of a surprise, but you can work through it as an exercise. In fact, I should probably assign that as an exercise. If the cut is on the positive real axis, then an explicit formula for the square root of x plus iy is given by this. And I imagine that Fortran respects these and probably chooses the top case. The cut on the negative real axis is more popular than the cut on the positive real axis, but it's a matter of taste, I guess. So let's see, maybe I should say something about these and with pictures. Let's suppose we've got this function f of z equal to the square root of z squared minus 1, which is the square root of z minus 1 times the square root of z plus 1. And now imagine that we put the cut on the positive or negative real axis. Well, if we, let's first go to, say the cut is on the positive real axis. So the cut is here. So in that case, this function, the cut for the function starts at plus 1 for this function, and it starts at minus 1 for this function. In other words, this function has this cut, this function has this cut. And And the happy thing is that over here, the two cuts cancel because you have to, when you cross here, you get -1 squared. And now, what about down here? Well, down here, everything's negative, so nothing is going on. On the other hand, if you cross here, you see you're crossing the cut for this function. If you cross here, you're crossing the cut for this function, but not for this function. And so you just get one factor of -1. And so that means that for this function f of z, with the cut on the positive real axis, the cut for the function goes from -1 to 1. Now the same thing happens if you put the cut on the negative real axis. So if we put the cut on the negative real axis, then what's going on? Well, for the negative real axis, the cut for the square root of z plus 1 function starts at -1, and the cut for z minus 1, well, that starts at +1, and so that one goes here. But now the cuts are, so you get a factor of -1 when you cross the negative real axis below the point -1 to the left of the point -1, and they cancel. So, but you only get one factor of -1 when you cross between -1 and +1. So in general, this function, whether you put the cut on the positive or negative real axis, this thing has a net cut from -1 to 1. So that's the cut. So that's the effective cut. Okay, I don't see any questions. I think I'm going to skip that, but you can read it, of course. So let's see, there are various examples here. All right, I better do one of them. Which one to do? Let's do the one with the figure, and let's do let us say the first one with the figure. Suppose we want to evaluate this integral. So this is an integral from 0 to infinity dx over x plus a squared plus times square root of x in the denominator. And we're choosing a greater than 0. So what's the situation here? Well, what we first do is we put the cut, so let me draw a line here. We're going to put the cut on the positive real axis. So let me switch to black, or let's go blue momentarily. So here are the axes, and we're going to put the cut on the positive real axis. So let me put our cut here. So there's the cut on the positive real axis. And A is positive. And we can think about what we're supposed to do, of course, is we're supposed to do the integral. We're supposed to integrate this way from 0 to infinity. So that's supposed to be our initial contour. And this, what did I call that? I call that I plus. So the integral along here is the one that is the original integral. On the other hand, we can define I minus as So let's see if I can do a different color. Let me do that. All right, well, I don't know what I'm doing. All right, let's do that. So this is I minus. And maybe I should say that the actual integral here, oh gosh, what has happened here? I seem to have, right, there's the thing we're trying to integrate. So we're trying to integrate I sub square root, which is integral 0 to infinity dx over x plus a squared, square root of x, a greater than 0. Okay, now what we've got here is that IS is in fact the same thing exactly as I plus. So IS is certainly equal to I plus. But we've defined a new integral I minus. And what is I minus? Well, it's an integral from infinity to 0 of this quantity. But now, what is x? Well, x is x minus I epsilon because we're below the real axis. And we put the cut on the positive real axis. So if we switch from x minus I epsilon to x plus I epsilon, we get a minus sign. Then if we use the minus sign to flip the limits, we're back to IS. So we get that IS is equal to, by definition, I plus, but it's also equal to I minus. And then we introduce two ghost contours. And so let me maybe I'll use yellow as a ghost contour. So we do a ghost contour here, like, but wait, my ghost contour actually stops. I went too damn far. All right, let me do a little bit of erasing here. So I'm going to erase that, erase that. Okay, I'm going to erase that. And now I have to, whoops, damn it. Okay, all right, now I've got a problem because I don't know how to get back to, I need to get back to the one that's called 97. Damn it. All right, I don't know, is somebody an expert with notes? Because somehow when I chose the yellow, it's not. All right, let's try it to be blue, but it's not saying 97, and I'm just worried that I'm going to get a. Oh no, it's okay. All right, so if I go back to yellow, then this is the contour that we're going to do, and then we're going to go like this, and then we're going to go out, and then down, and then we're going to hook up with the I minus contour. And what I see here is that I also have to do a little bit of erasing here. Actually, no, I should have. All right, hold on. Let me just. So let me see. We're going to connect here, and then we're going to connect there. All right. So now what we've got is a closed contour. We're going down this way, around this way, and it has this. So it's basically The rest of the contour looks like this. So we're going, let's see, we're going, let me just do the whole thing in yellow then. We're doing this whole contour like this. Well, I went too low. All right, so it's this way. All right, so that's a closed contour. And moreover, we can shrink the closed contour to a point without crossing any singularity. And in fact, there is a singularity, namely right here, there's a pole. Let me make that red. A pole here in red, and that's the pole at minus a that we're circling around. So that total integral is 0. On the other hand, so we have 0 is equal to, and in this, how did I talk about that? I said 0 is equal to IS, which is same as I plus I minus, plus I ghost plus, which is the integral up here. So this is I ghost plus, this is I ghost minus. All right, so let's make this a funny, and then plus IC plus, okay. So IC is this integral over here. And it's the integral clockwise around the pole at z equal to minus a. These two are equal. These two guys are both 0 because absolute value of z over absolute value of z plus a squared divided by square root of z, that's 0. So those ghost contours are 0, and these two guys are equal. And so in other words, the equation we get here is 2is is equal to minus IC, but minus IC is just the counterclockwise integral. And so we get that IS is minus a half IC, which is the so I'm just wondering whether I have a minus sign loose here. IC is clockwise, so this one actually is the counterclockwise integral, and the counterclockwise integral is, so it's 1/2 integral counterclockwise around of dz over z plus a squared, square root of z, about z equal to minus a. And so this would give us, this should give us pi I times the second derivative, or is it the first? It's the first derivative. This is the Cauchy integral formula of z to the minus 1/2. And so this is minus a half pi I z to the minus 3/2. And what is z? Z is equal to minus a. So this is equal to minus a half pi I 1 over minus a to the 3/2. So we can pull out the 1 over minus a, and we get pi I over 2a. So the minus signs cancel. And then we have 1 over square root of minus a. On the other hand, a was negative, and so this is pi I over 2 absolute value of A to the 3/2. Wait, what is going on here? A is negative, and so, all right, now I'm confused, actually. A is negative. A is negative, and so minus A is positive, so we don't really need the we don't need the absolute value because A is negative. So this is pi I over 2 A to the 3/2. Yeah, I guess that's right. But, oh, I've got an I, and I've got an extra I here. Well, I don't know. I'm going to puzzle this out. I'll tell you what, I'll send you an email or something. So I'm a little embarrassed that this thing is trickier than, apparently the correct answer is, here I'm taking A positive. What is going on here? Oh, I took A positive. That's right, A is positive. Sorry, I forgot that A was positive. A is positive, so this is minus A. Okay, so that's right, but this has to be an absolute value then. We have then, so then what we've got here is an I square root of minus A, and if we have the, this square root of minus a positive number gives us an I, and that I cancels this I. So this goes away. So let me get our handy eraser out here. So this is gone. And I don't, A is positive, so I don't really need this or that. And in fact, I don't need any of this then because we're done. A is positive. I somehow thought A was negative at one point. So it's pi over 2 A to the 3/2. Okay, well, sorry for the confusion there. Do we have any, no questions? Okay. So I don't think I need to do this one since we've already done that one. It uses the same picture, the same diagram. All right, so let me get now to conformal mapping. This, sometimes people think of it as something complicated, but it really isn't. So let's look at conformal mapping. Conformal, great. Conformal mapping. So what's a conformal map? A conformal map is Z goes to F of Z, where F of Z is analytic. And what conformal means is that the angles are preserved. Now, they're not always preserved, and we'll see when they're not preserved. And in order to work this out, let's just picked a particular point here, which I guess I called Z. And let's suppose we have a couple of, we have a DZ going like this. God, I thought I changed DZ, and I'll call that epsilon e to the I theta. And then we'll have a DZ prime, which I'm going to take the same distance, but a different angle, e to the I theta prime. So these angles I'm thinking of as from the real axis in the positive direction. So this is like, that would be pi over 2. This is maybe pi over 3, and this is maybe pi over 9 or something, I don't know. Anyway, now let's take dz prime over dz. Well, that's epsilon e to the I theta prime for epsilon e to the I theta. The epsilons cancel and we get e to the I theta prime minus theta. Okay, so that's the angle between these two, this angle here, that angle is theta prime minus theta, and that's what we're calling delta theta. So that's the angle in the z plane. So we're here in the, what we sometimes write as the z plane. But now we're going to set w equal to f of z, and we're going to look in the w plane. So z gets mapped into f of z, and so we've got some point here that we call w. And now we have a, when we do dz, we get a dw, and we're going to say that dw is equal to f of z plus dz minus f of z, and so that's equal to f prime of z dz. And so there's going to be a dw, and I don't know which way dw goes. Let's suppose it goes that way. And then there's going to be a dw prime, and dw prime is going to be f of z plus dz prime minus f of z. And so this is going to be f prime of z times dz prime. Okay. So now if we want to find the angle in the w plane, that's just dw prime divided by dw. And so this is f prime of z dz prime divided by f of z dz, f prime of z dz. The f primes cancel and we get dz prime over dz. Well, whatever the magnitude of dw is, it cancels. So, and it cancels because, well, dz prime over dz is e to the I theta prime minus theta. And that means then that dw prime over dw, those are of equal lengths, and moreover, the angle between them is the same. The angle here is theta prime minus theta. So what does that tell us? That tells us that as long as, so if f prime of z is not equal to 0, then the angles are preserved. And what in other words, this thing, we can call it e to the I phi prime over e to the I phi. We can call the angles in the W plane phi and phi prime. And actually, there are sort of two conventional ways of writing phi, and I use both of them here. And so let me switch back to using one of them, and so I'll write this as I phi. Okay, so this, in other words, is the same. So phi prime minus phi is equal to theta prime minus theta. So this theta doesn't look very good either. Let me see if I can fix the theta. Okay, so that's true as long as the first derivative doesn't vanish. And so if z is a point where the derivative of f is not zero, then then f is going to preserve angles at z. What if f prime is zero? Well, then you see dw. So let me just say if, and let me switch maybe to blue. If I switch to blue, if f prime of z is equal to zero, then dw is 1/2. Well, let me do df first. Well, dw, yeah, dw is going to be 1/2 fw prime of z dz prime square. No prime here. All right, let me put a prime over there. And dw is going to be 1/2 f double prime of z dz squared. So in other words, you do a Taylor expansion. So this, in other words, what this is f of z plus z prime, and this is f of z plus, that's dz. All right, so let me fix this a little bit. Oh boy, I went all the way to the beginning. All right, I can see this maybe is a little too long. Okay, so this is f of z plus dz prime. Okay, so we do a Taylor expansion of these two quantities, and now actually that's f of minus f of z, and this is minus f of z. So the lowest order terms cancel. The first derivative cancels by assumption, and then we have a second one. So now we have dw prime over dw is now equal to dz prime squared over dz squared. And this thing is epsilon squared e to the 2I theta prime over epsilon squared e to the 2I theta. So this is 2I theta prime minus theta. So if the first derivative is zero, but the second derivative is not zero, then the angle is doubled. And in general, if the first non-zero derivative of the analytic function f at z is the nth one, then the angles get multiplied by n. Okay. One amusing function that is analytic is the Möbius function, and it's AZ plus B over CZ plus D. And this maps straight lines into straight lines and circles into circles, unless AD is BC, in which case it's a constant. Right now we have a totally different topic, namely Cauchy's principal value. And this is really important in physics because we often have to deal with Cauchy's principal value. And it's a way of dealing with simple singularities like poles on the real axis. So let's define capital K as an integral from minus a to b, a and b both being positive, of dx f of x over x minus I epsilon. So what do we do? So this is what we're given. Now, in fact, this is not what you normally encounter in physics. You normally encounter something else, or sometimes you encounter this. It just varies. It depends. So let's first of all follow Cauchy or Cauchy, and do the following. Let me get rid of this stupid thing. It's the limit. Let's define it as, let's take this thing and rewrite it as an integral from minus a to minus delta, from minus delta to delta, and then from delta to b. So we got three of these things. And we're going to take the limit as delta goes to 0, but inside here we have the limit epsilon going to 0. But in the first and third integrals, since the absolute value of x is greater than delta, and delta is greater than epsilon because we're setting epsilon to 0 before we set delta equal to 0, before we take the limit of delta going to 0. In other words, let me just maybe, so in other words here, let me switch to a different color. So here what we've got is that delta is greater than epsilon is greater than 0. So in this integral and that integral, we can set epsilon equal to 0. And so we get these two things, but then we have to keep the middle integral. Okay. Now, Cauchy noticed that this was the really key thing that deserved a name. And so I don't know what he called it, but subsequently people call that the principal part of the integral of f of x over x dx. And it's defined as the limit delta goes to 0 of the integral from minus a to delta, minus delta, and then from delta to b of the same thing. So that's just a definition, and that's what's called the principal part. And the reason why it's a clever thing to do is that if the function f of x is continuous, then if you get close enough to x equals 0, it's a constant. It's whatever f of 0 is. And so then the large negative values of 1 over x for x less than 0 cancel the large positive values of 1 over x for x a little bit greater than 0. And the same thing can happen at any point y. So the principal part of the integral from minus a to b, a and b both straddling y, is the limit delta going to 0 from minus a to y minus delta plus the integral of y plus delta to b of the same thing, f of x over x minus y. And so if we use Cauchy's principal value, we can rewrite this k as the principal part plus this more complicated thing. And so we've got that k is the principal part of this integral plus a double limit. Now we're going to evaluate the second integral, and we're going to do that with complex variables. So what do we do? First, we imagine here that f of x is differentiable if it's a function just of a real value, a real variable, or all right, so it just, if it's a function just of a real variable, it is differentiable. If it's a function of a complex variable, it's analytic. In any event, we write f of x as f of 0 plus x times f prime of 0. Remember, the problem here is 1 over x minus I epsilon, not, there's no problem with f. We're assuming f is a nice function. So we can then split this into two integrals. The first integral, we pull out the f of 0, and we're left with just the integral of dx over x minus I epsilon. We just keep that all the way through, and then we work on this part. Well, we pull out the f prime of 0, and what we've got is the integral from minus delta to delta of x dx over x minus I epsilon. But again, we can now take the limit as we can take the limit epsilon going to 0 because we've got this x here, and x is well, we've got the x in the numerator. So as this thing gets, I mean, this is basically just the integral of 1. And so in the limit of epsilon going to 0, this is the integral of 1. And the integral of 1 is from minus delta to delta is just 2 delta. And the limit of that as delta goes to 0 is 0. So this thing disappears. And what we've got is this, the double integral due to the first term. Now we use the analyticity of 1 over z minus I epsilon. So instead of integrating straight from x along the real axis, we integrate along a semicircle that avoids the point x equals 0. We set z equal to delta e to the I theta, delta being greater than epsilon. And we let theta go from pi to 2 pi because so in other words, in pictures, let me just do this in pictures then. What we've got is we're going from minus delta to delta here. And we've got this problem here at the pole here is z is equal to I epsilon. So the pole is here, I epsilon. And what we do is we just integrate here. So originally we were integrating straight across here, but since this is an analytic function here, we can so I've gone back to the original form. K is principal part plus this complicated thing. And now we're going to deform the integral so that it's down here. And now we'll just do that integral. Well, the integral is theta goes from pi to 2 pi. So I'm putting if you want, I'm putting the cut on the positive real axis. Theta goes from pi to 2 pi. Z is delta e to the I theta. We can take the limit epsilon going to 0 because over here, if we took epsilon going to 0, we'd hit the real axis here. Whereas now, because we've deformed the path of the contour, the tiny contour integral, we can send x to, we can set epsilon equal to 0. And then when we do that, we just have 1 over z, and that's 1 over delta e to the I theta. dz is I delta e to the I theta d theta. The delta e to the I theta term cancels. we just have I d theta, and d theta is pi. The integral of d theta from pi to pi over 2 is just pi. So we have I pi times f of 0. So this is the important result, namely that the original thing, k, which was this funny integral, is the principal part of a simpler integral, but one that has a singularity, plus I pi, the value of f at 0. And the only assumption is that f is nice, which for practical purposes means it has a finite derivative at x equals 0. And so this is the thing that you will see many times in courses, in physics courses, namely that 1 over x minus I epsilon is the principal part of 1 over x plus I pi delta, or equivalently, 1 over x minus I epsilon is the principal part of 1 over x minus I pi delta. So you might say, well, why is it that if we had the opposite sign for delta, what happens? Well, the opposite sign for delta would mean that the extra term would be f of 0 times the limit delta going to 0, limit epsilon going to 0, integral minus delta to delta dz, 1 over, and now it would be z plus I epsilon. So now the pole is down here at minus I epsilon, and we're originally integrating here from minus delta to delta, so we're integrating along here. But then we say, well, if we integrate along that green segment, we can't let epsilon go to 0 because we get a 1 over 0, which is not good. And so what we do is we switch, and we now integrate over here from along this contour. And now we can let epsilon go to 0 because we're not going to hit the contour. So this thing becomes equal to f of 0, and we then have, we then say z equal to delta e to the I theta, and dz, of course, is I delta e to the I theta d theta. And since we're integrating along this blue contour, we can set epsilon equal to 0. And so we're taking the limit delta goes to 0 of the integral minus delta. Well, it's no longer minus delta to delta. So let me get rid of that for a second here. It is then an integral d theta from pi, whoops. From pi to 0, d theta, dz is I delta e to the I theta d theta, 1 over z, because we've set epsilon equal to 0, is delta e to the I theta. And so this is f of 0 times, let me switch from 0 to the limits. And if I switch the limits, I get a minus 1 d theta. And the only thing left is I, because the delta e to the I theta in numerator and denominator cancel. And so what is that? That's equal to minus I pi f of 0. So that integral is minus I pi. So we have the opposite sign here, and so we have what physicists write this often as x plus I epsilon is equal to the principal part of 1 over x minus I pi delta of x. And the idea there is that if you integrate f of x over x plus I epsilon dx, you get principal part of f of x dx over x minus I pi, the integral f of x dx delta of x. I wrote those in the wrong order, and so that gives us principal part of integral f of x over x dx minus I pi f of 0. And so that's what, so in other words, this term here, see, is the same thing as that term there. Okay, now there's nothing special about the point x equal to 0. And so the way physicists normally write this is 1 over x minus y plus or minus I epsilon is principal part of 1 over x minus y minus or plus I delta of x minus y. So that's one of Cauchy's many tricks. And as I said, it's one that physicists use a lot because we need to do actual integrals and evaluate things, whereas mathematicians can just say, well, it's a number. I guess a simple example of Cauchy's trick is, what is this integral? 1 over x plus I epsilon, 1 over 1 plus x squared. Well, it's going to be the principal part minus I pi, the delta function. Now this is odd. The principal part of this thing is going to be 0 because an odd function has no principal part. This thing is going to evaluate the function at 1 over 1 plus x squared at x equals 0. And so we just get 1. And so the answer is minus I pi. So this integral is actually minus I pi. These are some more examples. We have 3 minutes left. Let's do this integral, which is one that I promised you earlier. Is the integral from 0 to infinity dk over k of sine of k. And so the first thing we do is we write the sine as 1 over 2I e to the ik minus e to the minus ik. And then we notice that we're only integrating from 0 to infinity, but this one is the same thing as, in other words, we can rewrite the two of these as one integral. And now we've got something that looks like that, now we've got something that we can think of as the Cauchy principal part, in a sense. We can say that I of S is we're going to call this, we're going to take the principal part of this integral. And on the other hand, we now know that the principal part is what? It's the whole thing, in this case, minus I pi delta. And to do the first integral, we do a ghost contour in the upper half plane. To do the second integral, we just use the delta function. And actually we do the, let's see, we do the ghost contour in the upper half plane, the pole is in the lower half plane, so this thing is 0, so we just get pi over 2. Let's see, maybe that was too fast. We're out of time. So in other words, so the first thing we do, in other words, is we reinterpret the original integral as the principal part. And then we say the principal part is, in other words, we reverse this thing. We're saying here that the principal part of 1 over k is the is 1 over k plus I epsilon, and then I said plus I, all right, let me get this right. Oh yeah, right, principal part. If we have a plus I epsilon, then the principal part has a minus I delta over here. But if we put that over to the other side, we get plus I delta of k. So that's actually what we're using. We're using this formula, which of course is a special case of these, well, let's see, didn't I write it down? Right, it's a special case of the formula right above it. In fact, it's a special case of that. And we're using that to convert the principal part to this plus that. This one, we do a contour integral and we see it 0. This one, we use the delta function, we get pi over 2. Okay, that's how it works. We are effectively out of time by 2 minutes. I don't want to keep people here. Is there some question? Shoot it to me quickly on chat, or disguise your voice and say it in a disguised voice, and I'll try to answer it. If not, okay, we'll just quit. So have a good weekend, stay out of bars, and stay safe. And eventually this pandemic will be over sometime next year. Okay, so I'm going to stop the recording.